boundary condition of lead-driven cavity flow. I guess if internet connection is okay, I can show you the sample code, but it does not connect. This shows sample of boundary condition on this one is for top wall. I guess this part is difficult to understand for beginners. This line is top boundary of the simulation, and you have U component velocity, and this J index of this position is JE. But since we are using staggered mesh layout, this grid point is XJE. So mesh point and velocity component these two have the same index JE, but the position is different. This is dummy point. The index is JE plus 1. So to satisfy the no-slip boundary condition on the moving surface, if it is, this is inflow velocity, the velocity profile should be locally linear. If velocity on this place is this length, the dummy velocity should have this length. The definition is like this: U J E plus 1. This is dummy. It does not calculated in the simulation. And this one is first velocity point inside the fluid boundary. Its mean value should be a given velocity of the moving wall. Actually, you have two or more than boundary dummy points. They are so you have to copy this value to this one. You have to check the relation between the index, this one and this one. This one is dummy point. the relation between these index is like this. The index of dummy point and actual point inside the boundary. Its midpoint should be here. But you do not have actual definition point on the moving surface. But you can consider the virtual position. If U component is on this surface, its index should be between these two, between JE and JE plus 1. So it should be JE plus 1/2. So from these two conditions, you can find counterpart dummy points, its index, and also you can get the velocity of the dummy point in the similar in the similar equation. But you have to consider the difference of the position in V components. In B components, velocity point is here. This one is B J E, and this one is B J E plus 1. And next one is BJE plus 2. So the condition is slightly different. So I will not show the equation for this configuration. This is your homework. If you understand what is going on in the simulation, you can make similar. You can find similar relations between actual flow point and dummy point. Naturally, you have to also consider the position of pressure definition points. Okay. Then today's material is the Kelvin wave is, as I said, it is the pattern is observed. The pattern is caused by the concentration of wave energy. The pattern is complicated because wave on the free surface is wave of the speed of gravitational wave depends on wavelengths. I think last picture was drawn. I shown you this one, but it is in Japanese, so I found another one. The ship is going, and the Kelvin wave pattern is like this, and you can find the features in these pictures. Actually, just behind the ship, with the width of ship is occupied by turbulent wake. So wave pattern is not significant in this region. In potential-based applications, it does not consider turbulent wake, so this pattern is not obvious. instead, it shows very clear wave pattern. The potential in potential theory, they will consider a basic source of potential. It is Kelvin wave source. It is a two-dimensional calculation. If the basics is if you place infinitely small object on the free surface and move it, it will generate wave pattern. So this is element of wave generating source. Actual ship is we can assume the wave system around the actual ship is the superposition of small elements. This image is, or I guess this image is the result of Mathematica application. Its bird's eye view is like this. So this source has the basic feature of a Kelvin wave. The actual integration of Kelvin wave source is complicated. This is the basic formation of the source. However, difficult. It has position of the source and the density of the source, and alpha is the direction of wave propagation. We cannot go in the detail of these problems, but important point is this is it has very clear definition in mathematics, but actual simulation will be by numerical treatment. You have to use hyperbolic cosine and cosine in programming. In this case, although it is very clear in mathematics, getting the result is sometimes not stable because of the singularity of the equation. So the specialists in potential theory are good at dividing this equation to components to get stable solution. At present, we will only see the result of this kind of simulation. This shows more sophisticated version of potential theory. The previous one, Kelvin wave source is only placed in the reference axis, so it is only the if the shape of the ship is like this, small magnitude of source is placed here, and in the midpoint, the magnitude of source is increased. So the shape of the ship is represented by the distribution on this position. So naturally, this Kelvin wave source is very beautiful, but it is applicable only to simple solution. It does not represent. It represents only the distribution of the mass in one-dimensional distribution. So in actual applications, they are using boundary element method. This is only a sample of this treatment. Actually, the specialist in boundary element method can calculate more complicated situations. The basics is providing panel on the body surface. In this case, it is submerged body, submerged spherical body. You can make mesh, but this mesh is only exist on the surface. You can calculate the magnitude of source on each panel. So sometimes boundary element method will be called panel method. They will require it is different from Kelvin source potential. It requires another sophisticated mathematics framework. In this case, they will need the surface on surface panels on the body, and also they need panels on the free surface. If it is not a submerged body, it requires surface. Although in this picture it is not obvious. The true configuration of this one is you have one mathematically modeled ship shape. It is Wigley model. They have also panels on the surface, and also it has free surface panels. And in this picture, you can only see the bottom edge of the Wigley shape. The result is like this. It shows very realistic Kelvin wave pattern. But the difference between the BEM and other Navier-Stokes solution is existence of turbulent part. In potential theory, they do not reproduce turbulent wake part. In the previous one, in the actual phenomena, you will see turbulent wake part because it is caused by the viscosity. The ship will accelerate the fluid particle around the ship, and after the ship is going after the ship goes, the particle motion is still continued. So it will, if you will hide ship part, you will see the water jet-like structure in the fluid. Naturally, this part is not appear in this application. However, when you compare the result of potential treatment and other Navier-Stokes treatment, you will see this pattern is very vague when it is far from the body surface in Navier-Stokes equations. It is because In Navier-Stokes solution using mesh, the resolution highly depends on mesh size. So reproducing such a clear wave pattern requires very dense arrangement of computational mesh. However, it is not cost efficient. But in the boundary element method, it does not have any diffusive capability in the system of equation. So wave pattern is very clear even if it is far from the body surface. So if you want to know the clear wave pattern far from the body ship surface, boundary element method is a good choice. However, if you would like to know the detail of flow structures around the body, you have to use Navier-Stokes solution. Other difference is boundary element method or potential theory based method assumes wave height is significantly small. It is based on the assumption that wave is linear. It means wave height is infinitely small. So if it is if the ship speed is moderate, it is slow. If ship speed is slow, you can assume the wave amplitude caused by the ship is small. In this case, boundary element method gives very good solution. However, in high-speed ships or bow shape of the hull surface is slightly complicated. It does not show the feature of hull shape that does not show correctly. And the discussion is first discussion is on interface tracking method. It uses boundary fitted mesh. The example is shown here. It uses the basic method for interface tracking requires height function. Height function is like a map of isocontour lines. The function h, it has parameters of x, y, and t. So t is time. It shows time-dependent deformation of the free surface. If you specify the position, this function will return the wave height, free surface height. Naturally, this type of treatment does not express the overturning and breaking feature of the wave. Overturning is like this. If wave goes steep, it will show the overturning. When overturning happens, you cannot define a single value wave height function because in in this point, wave height is here, but in this point, wave height is here and here. So wave height function should have 3 values in this configuration. So this treatment is only applicable to moderate free surface motion. And also breaking wave is after the collapse of wave shape, it shows breaking. After breaking, energy of kinematic energy will affect to the surrounding from motion. Anyway, for a while we have to consider moderate motion of free surface. It does not have overturning and wave breaking. In the treatment, we have to consider the kinematic condition of free surface directly. The equation is like this. At present, what we have to know is the wave elevation speed of free surface. It is round dh, round d, round h, round dh, round d, round dt. It is the basis of this equation is the it is similar to convection term. If there is no convection, you have to consider only this part, uz. If free surface is moving, the speed is a velocity component of u of it is z component of velocity. So it is uz. But usually fluid have more horizontal motion. In this case, if ux is positive, it means flow is going in this direction. In this case, you will if the wave front is moving with this velocity vector, the next profile will be like this because free surface is moving in this direction. The effect is appears in this part. Velocity times slope of the present free surface. So you can imagine in this case if x axis in this direction, in this case dh dx is positive. If dh dx is positive and velocity is in this direction, the effect of ux and the slope of the free surface is leveling down the present free surface at this position. So this is so the function of ui part is also the same. So actually it is the speed of free surface elevation is uz minus horizontal component of velocity vector times gradient of free surface. And so the detail of the treatment depends on the scheme of computation. This shows one example. If you can calculate the speed of elevation at each mesh point, you can calculate the free surface position in the next time step. So you will change the position and regenerate the remaining part. It is also possible in boundary fitted coordinate. In this case, mesh is fitted to the surface of the sailing boat. Although it is shown in a two-dimensional shape, but actually it is a part of a three-dimensional mesh. In the simple situation, the mesh is moving only in this direction. This is simple image. But if you are using boundary fitted mesh, the mesh motion is like this. If free surface is going up, the mesh will shift gradually, and the free surface is fitted to the required surface motion. If free surface is going down, it will the motion of the mesh is distributed inside the domain. So this will produce this kind of appearance of free surface deformation. So these are examples of interface tracking method. In these approaches, free surface is always on a mesh surface. The other treatment is interface capturing. As I said, the mesh covers around the free surface. The most referred the paper on this field is marker and cell method. Usually we call it mark method, and it is by Harrow and Welch. This paper is very famous because it contains marker and cell method, and also staggered mesh approaches for the incompressible flow. So I recommend you to read this one at least one time. At present, we have to concentrate on marker and cell approach. The problem they solved is water dam breaking phenomena. Now, in many free surface problems, researchers are using these problems as a benchmark. The problem setting is in initial condition, water column is placed like this, and if we conduct this one in experimental tank, we have to provide a wall to place to keep this water column. But in experiment, the water column will be abruptly pulled up, then water column goes to break. But in numerical treatment, you do not require such a wall. You can only define the initial condition and start simulation. And in this case, shows the breaking motion of water column. What they did is to define markers inside the fluid media. The calculation of fluid motion is on the entire domain in this case, but they placed markers in the fluid media and tracked its path. In the initial condition, they define control. In this age, finite volume method is not known, so their definition is finite difference method. But they are using staggered mesh, and the pressure point is also in the computational domain. So the basic idea is place marker and calculate its motion. At first, this cell has marker and this cell does not. So you can assume the waterfront is here. But according to the time development, you can calculate the path of marker particles. In a time instance, you can consider this control volume is in the water because it contains one marker particle. So this motion of markers define the position of free surface. If empty control volume occupied by new marker, the condition of control volume will be changed from air to water. So you can, if you see this picture in detail, you can understand the position, the time development of marker positions. So this is the basics of interface capturing treatment. There are some development of the treatment, but most of the basics are already developed by these two. You can imagine the problem of this treatment because it does not. The marker is massless. It does not have mass. So sometimes markers concentrate in a small position, or although it should be fluid part, if density of marker, number of marker is insufficient, there might occur the control volumes. They do not have any marker points. So it does not assume the stability of the simulation. One solution is to rearrange the marker distribution. I'm sorry, I did not provide this picture yet. The previous one is for two-dimensional treatment. Actually, they proposed also three-dimensional phenomena. In the last class, I draw a very rough picture. I will draw it again, but more carefully. In three-dimensional case, the same approach is theoretically possible. Place the markers inside the fluid media, but naturally it is very time-consuming. So in three-dimensional case, they are using only marker particles on mesh points. And what they did is to calculate the particle motion but if you repeat this calculation, the surface is very distorted. So what they did is to interpret the motion of these particles to vertical motion. So based on the information, they calculate the surface the elevation, only the elevation of the surface. And these points are always above or under the original point. So it avoids the distortion of the computational mesh. In University of Tokyo, they have similar approach, but it has some new features. They call it Tokyo University Modified Marker and Cell Method. So abbreviation is TUMAC. In two-dimensional condition, Harlow and Welch used marker particles, but in this case, the group of University of Tokyo used the segment. Free surface is defined as the free surface is defined as a segment. It cuts the computational mesh. What they did is to calculate the motion of the segment. Segment vertex points. So based on this definition, the next segment will be like this. But in the treatment, we have to calculate the new cutting points based on this information. So I will draw the new cutting point in this color. Okay. So their approach is using segment represented free surface instead of marker. Also, they are using staggered mesh, so the treatment tracking of this segment is somewhat complicated. After getting information of the next cutting position, they will connect these cutting points by straight lines. So it will be a new free surface position. The merits of this approach is it does not the problem of density change of markers does not happen in this case. In MAC method, in some part mesh is concentrated, caused by fluid motion, and in some part density of the mesh is not sufficient. So providing uniform density of markers is leads to another problem. But in this case, in TMAC method, they are only tracking the front shape of the free surface, so this problem does not appear. And also, they can treat overturning and wave breaking. In wave breaking, this free surface front will merged in the next time step. Although it is represented by segment, so the actual representation in the computation is like this. If these two cutting position is in close distance, they can treat the merge of free surface lines. so it can handle the braking motion. I'm sorry, I will have the example of this simulation. Actually, I used this one when I was undergraduate student. Also, in the treatment, they considered the three-dimensional phenomena. In three-dimensional case, treatment is very similar to the 3D version of Mach method, but they are in Mach method overturning, three-dimensional overturning and braking is also possible. They will calculate the they will also calculate the motion of this point, but in this case, the motion is actually they are calculating the motion of these cutting points. So I guess the picture is almost similar to the previous one for Mach method, but the philosophy is different. Oh, I'm sorry. I should have more slides for these problems, but it is not sufficient. The Mach method and the 2-Mach method are using markers for tracking. So they are in this type. They are using massless particles or massless segments for tracking the free surface. The next one is transport equation of marker density or volume of fluid. It is similar to the conservation equation of mass. So in the last class, I showed the simplified example of VOF method. but in two-dimensional or three-dimensional cases, their treatment will be like this. It is divergence of mass similar to mass flux. It is the equation is the same as the mass flux mass conservation law, but in this case, rho is density function. Sometimes it will be called level set function, or I'm sorry, marker density function or level set function, and sometimes VOF function. The meaning of rho is to define the free surface position. This is free surface, and in fluid media, the marker function is the value of fluid media. Low water, and in this region, low is low air. So this convection term, this calculation of convection does not show any effect inside water media, because in the domain, rho is almost constant. So if it is constant, this part is zero. There is since in the FVM manner, going in and going out is always the same. So there is no change of marker density inside the water media. Also, if you conduct estimation in air side media, situation is the same. The only this treatment is only effective around the free surface. In this case, I draw clear free surface line, but it is not so clear in this treatment. In this case, water surface have thickness. In the center line, rho is equal to the mid value of rho A and rho W. This line is rho W, and this line is rho A. So in this region is water, and this region is air. So if a control volume is far from this front surface, this transport equation does nothing. But but near the free surface, this distribution of density is moving according to the fluid motion. So the actual the free surface is not directly seen as an image, but you can construct the position geometric shape of the free surface by calculating the iso value line or iso surface of marker density value. So the definition of free surface is rho is equal to rho free surface. This is the definition of free surface in this treatment. Actually, this is almost equivalent to the convection calculation. So convection term requires upwind scheme. As I said, upwind scheme shows diffusive capability for stabilizing the fluid motion. But diffusive capability is not good to keep the thickness of free surface. Because of the upwind scheme, this thickness will be expanded according to the time development. So it needs another consideration to keep the thickness of this region in a limited size. It will be discussed in the next class. Okay. Okay. Thank you very much. Do you have any?